Okay, so we're ready. 4 o'clock. I can go ahead. Okay. So welcome everyone. My name is Rees. I'm a DBA. I work at Pandora. I've been there for a total of, thank you, for eight or 9 years now. And we're going to walk through how our usage of Postgres has evolved over that time. So, in the beginning, there was no Postgres at Pandora. It was we were an Oracle shop. But this was a relationship doomed from the get-go. Irreconcilable differences. They wanted a lot of money. We didn't have a lot of money. And so on a Friday, we closed the business week as an Oracle shop. And the next Monday morning, we were a Postgres shop. For all the usual reasons. I'm not going to go into them here, but basically we wanted to go open source and scale out, and that really didn't fit in well with the Oracle solution. Right from the get-go, we knew we were going to be creating a great number of Postgres instances, a great number of clusters. And to try and add order before there was too much chaos, we came up with a set of predefined DBMS classes. So a class was defined by its Postgres configuration and by the HBA file, the host-based authentication file. So given those two things, we came up with about 5 or 6 different classes of databases. So when you would want to install a new system, it was essentially a wrapper around the initdb script, initdb program, which would present you an a la carte choice of the type of system you were deploying. So the first 3 are listed here. Nexus. This is where we generate music metadata. So this is our most upstream environment. It's a set of DBMSs. And it's our data ingestion environment. It's where, well, back in the day, we would get box after box of CDs delivered to the office. And it was some people's job, their entire job was to rip open the boxes and load the CDs and then rip the tracks on the CDs and forward them to our music analysts. Our music analysts are specialists in the music genome, which the music genome can be thought of as I think it was a multi-dimensional space, and every track is placed somewhere in that multi-dimensional space. One of the dimensions, for example, is beats per minute. So the analyst will listen to the track and determine how many beats per minute are in the track. Another dimension is voice. Is there voice on this track? And if so, is it a male voice or a female voice? And where on the continuum between a male voice and a female voice does it lie? And is it a breathy voice or a nasal voice or a guttural voice? Each of these things help position the track in this multi-dimensional space. And that's what we do in the Nexus environment. We take that data and then we mash that together with objective data, like the names of tracks and albums and artists, all of that's related together. We do a lot of deduplication at this point. Any given track, certainly with popular music, will appear on many or multiple albums. It may appear on the initial album, then a single. It may appear then on an artist's greatest hits or a compilation of like hits from the 80s. So we do a lot of deduplication. And the result of all that work is an export, a pgdump export. And that pgdump file is then distributed to our next class of databases called the music metadata class. So this is a massively redundant set of read-only databases. So anyone who needs music metadata will read from these databases. So, for example, you have your iPhone or whatever your listening device is, and you enter in the name of the artist you're interested in or the song you're interested in. So that string will make it through our system into our music metadata database, and we'll do a fuzzy search trying to find the some songs that we think you will like to listen to. We'll then pass that information back up the pipe, and we will download from our media servers songs that we think you will like. You'll start to listen to them, and then hopefully, if we've given you the correct music, you're going to start giving us some feedback in the terms of thumbs up and thumbs down, or if you don't like the tracks at all, you may start skipping tracks. All of that information finds its way back into the next class of systems, our radio class. This is probably our most critical class of databases, and is manifested as a set of sharded databases. At the moment, it's 16 sharded Postgres installations. We shard by listener ID. So when you become sign into Pandora, you are given a listener ID, which is just an arbitrary integer number. And then all of your information is stored on one of these shards. We had the data warehouse class, which unfortunately is no more, underfunded, understaffed, and abandoned, and replaced by Hadoop. So we probably now have more Hadoop hosts than we have people in the company. And it was recently mentioned to me that we have approximately 32 cores for every man, woman, and child who works, 32 Hadoop cores for every man, woman, and child who works at Pandora. And we have about 2,000 employees, I would guess. So the information from radio finds its way into the new data warehouse, which is no longer Postgres, but which is Hadoop. And finally, last but not least, is the cluster class. And there is no E in our cluster. It is our in-house developed high availability distributed database. It's something we built based on problems we were having in keeping systems available in the read-write mode. If you have any questions, please interrupt as I'm going along here. So when I came on board at Pandora, we weren't really doing much in terms of monitoring Postgres. We had the typical Nagios alerts deployed and in place, but they did not much more than check that the service was running, that there was adequate disk space, and that replication wasn't lagging by too much. So the first thing I undertook was to implement monitoring. And of that, the first thing we did was monitor current activity. And this is some of the low-hanging fruit that I picked straight away. Monitoring errors, that is looking at the Postgres log file for errors, just seeing what sort of errors are occurring. And then for each error, drilling down on that, is it significant? If it's not, then we can start to filter the error out, and so we don't get alerted for errors that aren't particularly important. So the original monitoring was done by scripts we developed in-house. Now we're starting to use that combined with a utility called Tail and Mail, which is a general log processing program. As well as the errors, we looked for long duration queries or the long query log, long duration transactions. We actually terminate transactions that exceed a threshold. So we negotiate that with the owner of the application and decide upon some threshold beyond which we will unconditionally terminate their process. We also monitor for blocked processes, and we use two-phase commit protocols. So in Postgres, that manifests itself as prepared transactions, so we have to keep a control on that. Because if the transactions are started and not committed, then they end up holding locks. In our particular application, long duration transactions aren't particularly important because the only thing you would be blocking is someone else trying to update the record for the same listener ID. And that usually only happens when you're sharing your account with a family member. So if there was something along those lines that both you and say your spouse or your children were using the same account, and we may try and then update the same listener record at the same time, and one of them would be blocked if the transaction was out of control in terms that it had been perhaps orphaned from the client. As well as monitoring for errors and long-duration transactions and queries, we also monitor their frequency. I found out the hard way that increases in frequencies of errors and frequencies of long-duration queries are indicators that something is amiss in your system. So it never ceases to amaze me that we've been doing this now for a decade, and yet after our weekly code pushes or our bi-weekly code pushes, we will see increases in these metrics because something has fallen through the cracks. For example, we have a tendency to try and DOS ourselves based on creating too many connections. We'll lose track of the number of connections we're doing and generates a self-inflicted DOS attack. Also, through hard-won experience, it's worth also monitoring syslog because you can correlate that back to issues you see in your Postgres logs. For example, a sudden increase in the number of long-duration queries can map back to a timeout at the hard disk level. We went through a phase of having lots of hardware issues, and we could very quickly map it back by monitoring syslog as well. As well as capturing current data, we capture short-term historical data. By short-term, I mean we keep it around for about a duration of about a week. And we have these infamous Snoop utilities that go in, and for every Postgres installation, we'll run queries against pgstat activity, pgprepared transactions, pglocks, and we'll count connections by client, by username. So we just get a feel for what's happening, what's normal. So we can identify what's normal. Therefore, we can then more rapidly identify abnormal situations. Continuing this further, we capture historical data. When we keep this indefinitely, we have a historical database to which we are continually scraping all of our Postgres installations, and we're feeding data back to this historical database. So for every Postgres instance, we go out and we run a query against PG settings, and we bring that data back and we store it in our historical database. We keep a track of the size of PG data, the entire cluster instance size. And then for every database on that Postgres cluster, we gather statistics from PGStat database. We also gather the size of the database and bring that back. And then for every table and for every index in every database, we capture that information and bring it back and store it in a central database. This is all automated on a daily basis. So what does this do? Well, it enables us to do these sort of things. Typically, people come to us and say, what was wrong with the database yesterday? And so we can go back and look at our Snoop output files, and even if we can't tell them what was going on specifically, we can show them, well, there was nothing wrong at the database level. Everything was behaving within expected bounds. So the problem that you saw is probably centered elsewhere. We also have built now a set of comprehensive alerting based upon our historical database. We have alerting based on change, and we have alerting based on rate of change. So every time a database is reconfigured, that is, someone perhaps has changed the number of concurrent users or the amount of shared buffers allowed, any configuration change will generate an alert, and we'll get a message saying that this configuration has changed. May not be a bad thing, but it was put in place originally because back in the day, configurations were distributed by our system administrator team, and they would often inadvertently push out the wrong Postgres configuration. So that started a time bomb ticking, and at the next SIG hub sent to that server, we would load the new configuration. So by having an alert based upon change of configuration, we got a heads up that there might be some performance issue on that DBMS. Sometimes it was a minor problem, other times that we may have totally broken replication because the wrong configuration was deployed. So we can see we get alerts on change and we get alerts on rate of change. So for all the major tables in all the major systems, we track how many rows are inserted, updated, deleted, and beyond that, we track the number of connections to the database per user, per unit time. If any of these change outside of accepted norms, we get an alert. And we get actually a graphical representation of the change so we can quickly eyeball, is it a significant change, is it not a significant change? And finally, we can do things like growth projections. When do we need to order more hard disk for this machine? Do we need to reshard our system? How much leeway do we have at the current rate of growth? For many years, the answer was easy, and the answer was we're going to double the size of everything in the next 12 months. And in many systems, that is still true today. Backups, let's move on to backups. Originally, they were all done by system administrators, and they always used pgdump. Lately, as we've staffed up in the DBA area, we've taken over the backups, and we were using pg-based backup. Little background on each of them. pgdump really doesn't work very well in many of our situations. It's slow to generate, and the major problem is restoring a database. It takes too long to restore it if we ever had to. Our mandate is only for a full backup every day. So although pgdump can generate the backup, if we have to restore it, it would take too long in most cases. pgdump has its problems. It can be blocked, and it can block other processes too. So it's you have to be very careful in running pgdump. It's more complex than you would originally think. When we switched over to streaming replication from our original Sloaney-based replication, we started hitting the conflict with recovery error that I think a lot of people you would have encountered. And so on systems where we have to take pgdump backups on systems that we are replicating using streaming replication, we will actually stop the replication, pause replication, take the backup, and then restart it when the backup is done. This leads to an edge case blocking, whereby if you pause replication at an inopportune time, it will actually hold a lock on an object, exclusive lock on an object, which will block your pgdump from the backup from starting. And of course, you don't know that's happening because you paused replication by intent. You've also disabled all your alerting based upon delayed replication. So you don't get a notification that things aren't working until the next alert comes in and says, hey, we didn't have a backup for this database today, what's happened? And then you go and see, and you can see your pgdump has been blocked for 12 or 14 or 16 hours on a paused replication. But I should go back. But all of that said, once you know that the limitations of pgdump, and if it's still okay for you to run in your environment, over the many hundreds of pgdumps that we've done, we get over a 99% success rate. In fact, very close to 100%. The only thing that we fail on is typically space, if we run out of space to do the backup. We've now switched to PG-based backup, and on all our new systems, we generate standalone PG-based backups, but even PG-based backup, which we initially thought would be easier to run than pgdump, has its own problems. We like to generate a self-contained backup, which means we want to stream the transaction log as well as the data. And in current versions, you cannot do that and write everything out to a tar file. You have to do a two-step approach. You have to copy the data to a directory, then tar up the directory. This is fixed in version 10, so it will resolve some of the space issues that come with running PG-based backup. We also have issues with the WAL file being removed before the backup is complete. That's addressed in version 9.6, which doesn't help us at the moment that most of our systems are on version 9.5. 9.6 PG-based backup supports replication slots. And a final problem we weren't, or certainly I wasn't expecting, is that the PG-based backup connection to the database may be terminated when the database you're backing up is under load. So both the streaming of the WAL files and or the data files may fail because the database is under load, under stress, and you lose your connection. This is compounded. PG-based backup doesn't seem to detect the error very quickly. Certainly not for the WAL file. I've seen cases where the WAL file streaming fails very early in the process, and the error is not detected until the end of the data streaming phase. And even errors in data streaming take over an hour sometimes to be detected. And PG-based backup doesn't retry, so you have to start again all over. I ran a query last week over all the databases we backed up ever since we recorded this. We record all of our backups for SOX compliance, and we get about a 98 to 99% success rate for PG-based backup. Most of the systems back up correctly without any problem most of the time. It's the same small subset that fail, and they fail because of the unpredictable heavy load on the database that we're backing up. And as I say, we're very lucky that we don't have to do point-in-time recovery because there would be other issues that would make that very difficult for us, and I'll come to those later on. We use replication, and always have used replication for a high availability solution. So we have all our production databases are replicated. We have a local replica. We have a remote replica called our disaster recovery or DR replica. And operationally, our first option is to fail over to the local replica and only fail over to DR when there's an outage that affects both the local primary and the local replica system. And again, our standard procedure when failed over is to stay in read-only mode on the streaming replica. I don't think I can ever remember a case when we actually promoted the replica to a primary. Originally, all of our replication was Sloaney based. Sloaney replicates tables and sequences only. We had hub and spoke and cascading topologies. It was a very, very intrusive replication system. Trigger-based replication, it adds its own triggers to your system. It disables your triggers, which can really impact you when you try and, if you run a PG dump on a Sloaney replica and you restore that PG dump, your triggers are disabled. And a lot of people aren't aware of that. So your referential integrity may be broken. It had a major effect on our release engineering group because they had to be very aware of the execute script Slonic commands, very intrusive on our operational procedures. And of course, the increase in writes on the production database, threefold increase in writes. A fragile system tended to fall over Sloaney tended to fall over at the most inopportune times, typically when we're pushing out new schemas. There was a small but perceptible replication lag, but it had a very, very good attribute of being able to replicate between different versions of Postgres. And so you can do minimal uptime upgrades of Postgres from one major version to another using Sloaney replication. And for my sins, I've had to do that on our radio system twice. On such a big system, which is like 16 shards, each one having a master and 2 replicas, and to go through that whole minimum downtime upgrade procedure using Sloaney from beginning to end was about 5 or 6 months procedure. Just having 2 or 3 new boxes to integrate into the system. Upgrade to the new boxes, take the old boxes, reprovision them as the new boxes for the second for the second shard, and then re-upgrade the second shard, and then keep cascading the boxes down the system. So we were very happy to jump onto the streaming replication bandwagon. After all, it has to be better than Sloaney, right? And in most ways it is. It's been a great boon to our release engineering. It's now a lot easier to push out changes. But we've had a lot of trouble with wall shipping in our highly volatile databases. We can generate wall files out the wazoo. Replication slots are our savior, though. Unfortunately, a lot of the systems we've deployed are don't support replication slots, so we have to ship wall files. Streaming replication is cluster-wide, not object-wide. Compare that to Sloaney. It's not as intrusive. We were caught unprepared when the archive command doesn't work on replicas, so we thought we were going to go to a cascading replication, but decided we didn't do that because we couldn't support replication by copying the wall files down the cascade. And of course, the other major thing that got us is that you can only replicate between Postgres versions, the same Postgres version. So my original thought was, well, now we've got streaming replication, we can just go to the downstream replica. I can upgrade it to the next version of Postgres, and if everything works fine, I can work upstream to eventually getting to the master and then upgrade that one. But no, that doesn't work. And of course, you may break some of your procedures because now that the replicas are now streaming replicas as opposed to Sloaney replicas, and you get the conflict with recovery error. So. Yes?
When you say wall stripping is a major source of pain in volatile databases,
yes.
can you elaborate a bit more?
Yeah, I will get it. Basically, it's the volume. It's the volume. We can generate a large number of wall files in a very short time, which can fill up the disk space on the master, and it means that the replica is maybe way behind. Maybe. So at about this point, we looked at our replication, our high availability solution using replication, and we basically defined out its shortcomings, where we had high availability, but in a degraded state, in a state whereby we had read-only availability, not read-write availability. And I've itemized the major ones up here. For example, when pushing out a schema change because of the locking required, that the schema change may be blocked by current activity, or we may block current activity by pushing the schema change, so we have to put users over to the replica. If we need to upgrade Postgres to the next bug fix version or the next major version, of course, you have to switch your users to a read-only replica. If you want to test a new version of Postgres in production before committing to it, that's quite difficult to do. The only way we could do that at the time was to use Sloaney or some similar product that could third-party replication product. And what if we get the typical maintenance thing where you've got a failed fan some memory you need to replace in one of your boxes. You have to shut the box down, open the box up. Well, of course, you have to fail over at that time. And the elephant in the room, about 5 or 6 years ago when we were looking at this, was we're going to have to reshard pretty quickly. We're going to have to move all our data across a new set of boxes, reshard it, because the volume of data is just too great, and that's going to involve significant downtime. And so we thought, well, wouldn't it be nice if we could do all of this stuff without any interruption of service? That is, if we could keep in a read-write mode continually. And last but not least, if we could do this on our schedule. Even with minor changes, one of the big sticking points is you've got to get people to agree to when you can shut the system down, when you can go to read-only mode. And so if we could get to a system whereby we could make these changes on our schedule, that would be great. So what we did, we came up with our own proprietary in-house developed product, and we've called it Cluster without an E, not to confuse with the Postgres cluster and the Postgres cluster command. We have yet another cluster. The compromise that was made is this is a non-ACID database. So if you need ACID compliance from your transactions, this is not a solution. The unfortunate truth for most of our applications, unfortunate from a relational database bigot point of view like mine, is that a lot of our applications were really treating the database as a set of flat files. So a lot of our systems can be easily migrated to the cluster architecture. So it's a high availability system, so we will compromise consistency for availability. It's an architecture intended for sharded databases, though you can have a shard of one. That means so you're not really sharded. How am I doing for time here? Am I doing 20 minutes? Okay. So in cluster, what we normally refer to as a shard, in cluster it's referred to as a group. And each group has 2 or more databases which are kept in sync by the cluster application. So this is a schematic, a high level, almost a cartoonish version of cluster. So the application will issue a write request, think of it as an update, that will go to cluster, and then cluster will send that update, or the write object A as it's written here, to each of those 3 blobs on the right. Each of those blobs is a Postgres database. And similarly for a select, if you bring back a row, cluster will request the data from each database in the group and then return that to the application. So this is the sort of a sunny day solution, and in real life, when you request a row or when you attempt to write a row, it may not be able to get to each database. It may be a connectivity issue. And when you bring the row back, each database may not agree on what the current value is for each of the elements on the row. So there is a read reconciliation process. I won't get into that now because I want to go through the whole process first. I will address questions on that later if we have them. So the write is split up into each of your constituent databases, and the read fetches from each of them. Hopefully they're consistent, and we'll send back the consistent value. If they're not consistent, we will run a set of tests to give you a consistent value. So let's look at some of the attributes of cluster. So 1 or more group members may be offline concurrently. By offline, I mean that it's offline from a cluster perspective. The Postgres is still up and running, but now we can address some of the issues we had before. If we want to push out new schema changes, we can take 1 member of each of our groups, and we can take that 1 member offline, and we can push the new schema to that database without any fear of being blocked by any user or without any fear of blocking any user. And we can do this at any time. We can do it in the middle of the day. Previously, we would have to do this at night or in the late evening when usage was at a minimum. When the upgrade has gone through, we rejoin the cluster. Cluster will catch up the database that we've upgraded. It'll heal it, it'll bring it up to date, and when it's up to date, it'll put it back into service, so it'll start taking real-time user connections. So we can do code pushes, we can do the case where we have to do some hardware maintenance, where we have to shut down the box for some reason, like replace a fan or whatever, replace a card. Totally transparent to the application. When the work is done, we just rejoin the cluster, automatically heals, and we're back online. Let's look at the next major bullet point. PostgreSQL version agnostic. Each group can be running a different version of Postgres. Each member of each group can be running a different version of Postgres. So if we want to upgrade to a new dot version of Postgres, a new bug fix version, we just pick one of the members of the group, take it out offline from cluster, stop the Postgres DBMS, put the new binaries in place, start up with the new binaries, rejoin the cluster, and we're done. Again, no interruption in service, no user knows about it. We don't even have to notify anyone, we just go ahead and do it. Similarly with, if you want to do, is my application going to run against the new version of Postgres? We can actually take one member offline, upgrade to the new version, whether a dump and restore, or you want to do an upgrade in place. Do that, bring it back online. You've now got your application running on just one member of a highly sharded system running against the new software under a real production load. Again, you can easily back out if you need to do so. Low risk, very high return. It also encourages us as DBAs to automate this process, because we can now just take one member from each group and we can run automated scripts on it to upgrade it. If we fail, well, we fail. We've still got 2 or other members that are active. We don't have to concern ourselves. And the other big bullet point that we have there is cluster supports transparent resharding. So you can add more groups to an existing system. Not only can you add groups, but the data is automatically rebalanced across those new groups with minimal impact upon current users. So this process could even take weeks if needed to be, but it doesn't impact current access. And you don't have to double the number of, there's no need to have a geometric increase in the number of groups either. You could start with 4 groups and just add 2 more groups, so in which case the data is spread out amongst the 6 members as opposed to being equally distributed among 4 members. But there are some disadvantages, some things that aren't supported yet. Joins are not supported yet. Neither are sub-selects, and neither are the with clause queries. Referential integrity is not there. So what you have really is a flat file database system. And there is an overhead, an additional overhead. There are 5 extra fields added to each row. The purpose of these fields is reconciling the record in case each member may have different versions of the data. So we need this to help reconcile records when there's a difference between them. And also for telling us which group a particular record should be in. And it also, one of the fields is used to let us group related data together, to always make sure that that all the records having this key will be on the same group. With us, that's the listener ID key. We want all the information related to the same listener on the same group. No matter how or when we reshard our system, that all information related to the listener must be on the same group. As well as being Postgres version agnostic, Cluster is in fact DBMS agnostic as well. You don't have to use PostgreSQL. You could use any other DBMS vendor. Not that we have ever used any other vendor, because we're very comfortable with Postgres operationally, and we are very, very confident in it from a reliability point of view. So that is Cluster. We actually use streaming replication to add an extra level of safety, so that we will replicate using streaming replication every member of every group. So if we get a failure, if we get a catastrophic failure of one member, we can rebuild it from the replica. Yes, there was a question?
Is the cluster node itself a single point of failure, or is that?
No. Cluster, the cluster app itself runs, there's an instance of it running on every member. So there's not one centralized cluster app. It's distributed. So every node that's got the database running on it also has a cluster instance running on there.
And are they all the same, or is there like a coordinator?
No, there's no coordinate. There is a coordinator when we do resharding. One of the nodes is nominated as the master, and it will instruct the others to now start reshuffling your data. Go look at your data. Go see, do you have any data now that no longer belongs to you? There's a centralized mapping metadata that we push out. And so after we reshard, we say, look, we've resharded. Go check your data at your convenience. Don't do it too intrusively, but go look through your data. Is there any data that you have on your local database that no longer should be there? If so, move it to where it should be.
So then at that point, how do you achieve high availability?
The system is still up all the time.
Yeah, but if you're connecting into the one of the cluster.
The data is in two places at the same time. When we're resharding, the data exists in more than one place at a given time. Where it should be, we try and get it to where, if it's not where it should be, we'll find it where it was before, if that makes sense.
Okay. But if your cluster app is dead on any given node that you're connecting to.
Well, if your cluster app is dead on that node, there are 2 or maybe 3 other nodes in that same group which have the same data.
Okay, but you're connecting it on an IP. So do you have like a floating IP that you float across the group?
No, I see what you're saying. The app will reconnect to another member that's still active at that time. Yes. Sorry, I misunderstood your question originally. Some of the scaling issues we've had, coming back to the wall file issue. So we do streaming replication supported by wall file shipping. We have volatile systems that generate wall file backups at a rate of about 150 wall files a minute. And that can be sustained over very long periods. And very quickly you can build up over 1 terabyte of wall files within 7 or 8 hours. Compounded by the fact that the streaming replication is keeping up. The replica is current with the master, but the shipping of the wall files is delayed because we just cannot copy or sync those files across the network quickly enough. So we have to go in there and take some drastic action and basically run PG archive cleanup to remove files that are no longer needed. It does involve some DBA intervention at that point. But we've been saved by the introduction of replication slots. Once you have a system that's using a Postgres version that uses replication slots, then you no longer have to copy the wall files over because they will be kept on the master system until they're no longer needed by the client. And with vacuum, similar issues. Transaction ID wraparound is a big bugaboo here. That once it starts, not much you can do about it. We have a very small number of systems that impact us. We can go from nothing to transaction ID wraparound within the space of 2 weeks, and it'll take us more than 2 weeks for the transaction ID wraparound to finish processing. Prevents utilities like PGReorg and PGRepack from finishing, because we're just changing data at such a rapid speed that they can't catch up. Those of you who may have used PGReorg and PGRepack know it creates temporary tables to compensate for the data fragmentation in the main table. And we have cases where the temporary tables created by PGRepack themselves are subject to transaction ID wraparound processing. So it's a no-win situation at that time. You have to pull the plug and brute force stop PGRepack. And again, auto vacuum, will run for a long time, like well over a week. Backups, depending on your recovery point objective and recovery time objective, that is, how long you can afford to be down for and how much data you can afford to lose. PG dump and PG restore are pretty impractical in most cases if you have any sort of large size issues. Even using the parallel options that have recently become available, the degree of parallelization is constrained by the number of large tables that you have, and we have a lot of systems with a large number of small tables and a small number of large tables, and so you're really blocked by the large tables. PG-based backup, the disk-based hog is the big problem. Hopefully that's addressed in version 10, where we can write the whole thing to a tarred-up file. At the moment, you have to write it to a directory, which takes a lot of space. Then you have to tar and compress, and the latter phase takes a lot longer than the actual PG-based backup. And we also have the issue with running PG-based backup on a system that's under load, that the backup will fail because the connections are lost. Some numbers. I don't really know how many Postgres clusters we have. I'm certain we have at least 1,650. I think we have significantly more than that, but probably a year or two ago, most systems were deployed by system administrators, and they didn't always log what they deployed. So unless I have some software to sniff all systems, I can't tell what's out there. And we have those 1,650 Postgres clusters have at least 335 terabyte of data maintained in them. And just radio itself, the advertising supported radio application is increasing by 2 terabytes a month. Let's see. So in summary, what I've learned from being at Pandora for like 8+ years and having to keep these systems up and running, you need to monitor, and monitor again. You have to current activity, watch out for increases in the rate, in the rate of errors, in the rate of long-running transactions, in the rate of long-running queries. Really, really drill down on those as soon as you can. It's not sexy, it's not rocket science, but I've found through hard-won experience that you keep those things under control, you will keep your system stability and reliability at a much higher level. And along a similar vein, capture metrics. Okay, they help for postmortem, but they also give you a good idea of what's normal with your system. Is it now behaving within expected ranges? And it helps you on projections for the future usage. and keep looking at you. What are you monitoring? What metrics are you capturing? What was the right thing to monitor last year maybe is no longer a valid thing to do. And you may want to capture new metrics. Okay. And I feel I've talked a lot and said a lot in a short time, but that is the end of the presentation. So thank you.